Okay, good morning, everyone. Let's try to start. Algorithm success, while no success, keep trying. If you're dead, now you can take a break. Pretty bleak. Yeah. And let's do the same format as yesterday. Let's have a lecture slides and some visualizations and maybe show you some codes. Okay, today's topic would be hash tables, stacks, and queues. Okay, let's start with having a list of grocery items. Okay, let's say you work as a cashier in the grocery, and you have this list of items. You have here, hair, have milk and eggs, and those are the prices. And right now, we can say that these items are unsorted based on their name. Okay, so the first thing we do is we try to sort them by alphabet, right? So now you have egg, milk, and hair, and now the prices is still associated with the certain, let's say, string or key. And the next thing we do is we can actually store them in an array. So as a cashier, you can easily look up, let's say, in an array of grocery items, right? However, not yet however, there's two ways to look at it. Let's say you have a list and someone comes up to you and pay. Let's say there's no computer system yet. And you have a book, a list of grocery item price list. And you can either search them linearly, one by one, item by item, or binary search, like a phone book, okay? However, customers would really get angry and annoyed because that would still take so long. We keep flipping pages, checking where the prices are. So we will now proceed to creating a hash table. So hash table basically is, think of it like a dictionary with fast access. Think of it as someone that when you ask something, he knows the price already. Like the people who wins and prices right, I guess. So thing is, again, binary search takes still a bit more steps, a few more steps, but let's try to do something called hash functions first. So what we do is we take an input, let's say a string input, just use the value and convert it to number. Okay. For now, think of it like that. If you have a hash, it just means that you take an input, you produce a different output. Also, it's related to like cryptography and data indexing and compression, checksum generator. Okay. So you converted x to the number 3. You converted milk to the number 0. You converted hair to the number 2. So now what do we do with those? So now we have an array again. Instead of the previous one, just putting them alphabetically, we have to either linear search item one by one or binary search, keep dividing and checking the middle. Now, what we can do is in our array is we can now map whatever the value of the milk from the hash. So going back, milk has the value of 0. And let's say the value of 0 pertains to the index 0 in an array. And now we can store the price. Okay? Same thing goes with the pear and eggs. So basically what happens now is if you query milk, you get the number 0. And basically if you get the number 0, you access this part of the array. So that is much faster because you just ask for a certain string, gives you a number, and gives you the exact location in the array. You don't have to search through it, okay? Another example for hash tables is, let's say you have a library system, and when you go to the library, they have this index, I think. So it's categorized based on category. And you don't have to go through all of the sections in the library. You just go, okay, I want technology. I just go to this section, and then now I can easily access all the technology groups. Okay? So let's also try to visualize this. So let's say we have a key value pairing, an index in the book. And let's say in the 200 section or 500 index number, we have the category of science. Okay? Let's say we want to add a book there. So let's put a book called Introduction to Physics. And now we see the other index are still empty. That means we still have no books for them. Interestingly, also with hash table, we can encounter collision. So now your problem is, what if I have another book and I want to put it on the same index, right? Will it overwrite it? Yes, it may, it can, it would overwrite that. So the way hash table works is, inside of that is you would have a list of key and value pairs. And we'll talk about linked lists tomorrow. But basically what this does is, if I add another book, instead of just overriding this index, I would create another key value pairing. And what happens is, this Introduction to Physics just points to the other book, and so on, and so on. And one thing we have to be aware of, as your hash table grows very large, it could also run in O of n, meaning n number of times, whatever the length of your list is, instead of the O of 1, which is constant time access, which is fast. Okay. Blah, blah, blah. So again, here how it works. You have a string, and you have your hash function. Basically, just computes, gets a string, spits out a number, and in that number we can map it to, let's say, an array. Okay. Time complexity for hash table. Again, on average, it's super fast, constant time. Worst case scenario, does not happen all the time though, is O of n. And space complexity is O of n, because your size of the hash table is the size of your items. Let's see more examples that you can use with hash tables. A perfect use case for hash tables would be when you go to a website, right? Let's say google.com, and it maps to an IP address. So basically, a perfect use case for hash table is this process called DNS resolution. Okay, putting a string and you're getting an IP address. Another way to use the hash table is, let's say you're running a voting booth, and basically your program just, what it does is it checks if the person have not yet voted. If yes, let him vote. If not, kick him. And again, if we do this in the, let's say an array, we keep, let's say we're at the 1 million voters, and there's the next voter coming in, it will be running so long to check everything first, and then check if he's in the list, and then if yes, don't let him vote. With hash table, again, we can just check if this string exists. If not, let him vote. Okay, voting. And you can also use this as caching. Okay. Okay. Next is, we go back to, oh no, we're not yet done. So recap, a hash table is basically a data structure that implements an associative array, abstract data type, a structure that can map keys or strings to values. Okay. So what is associative array? Think of it like a map, symbol table, a dictionary, basically an abstract data type composed of collections of, again, we repeat this, key value pairing, such that each possible key appears at most once in the collection. Okay, tries to avoid duplication. Okay, it is an array, a hash table. Again, another definition is an array combined with a hash function that separates each key into a separate bucket of the array. So what happens now is index 0 is a bucket, index 1 is a bucket, index 2 is a bucket, because you don't only have one thing there. A hash table uses a hash function to compute an index. Okay, you put the string in the hash function, and it spits out a number, or it becomes, you can use it as your index, also called as a hash code, into an array of buckets or slots from which the desired value can be found. Okay. And we do have codes for implementing a hash table, but most of the time I don't think people really ask us to create our own, because it's already implemented and they're built in. And most of the time, I think classes are just focused on using the hash table in solving problems. Okay. Let's go to stacks again. Very, very easy. It's basically, let's say, a stack of dishes, a stack of pancakes. You have the push, pop. You can also create in your own method to check the top and not pop it. You can also create another method to check if the stack is empty or not. Okay. A stack is an abstract data type that serves as a collection of elements with two principal operations: push, which add an element to the collection, and pop, which remove the most recent added element that was not yet removed. This is very, very similar to arrays. So again, you can implement a stack using arrays. So when you push, let's say in other programming language, you put it in front, which is, if you flip it, it's just on the top of the stack. However, we use stacks to use this limitation so that we don't use the random access. Going back to this stack is you don't really get to access this part unless you pop stuff. It uses the last in, first out. If you want to confuse yourself, you can also do first in, last out for stacks. Time complexity, O(n), meaning the number of length, the items. Insert and deletion is O(1), because it knows that it should insert always in the front. And deleting as well, when you pop stuff, it knows that it should be always on the top, right? So even the worst and average, they're the same. Space complexity, the number of items, that's the size of your stack. Queues, queue of cars. Basically, it's last in, last out, or first in, first out. And the terms that we often use for queues is, if you put something from the back, it's NQ. And if you remove something in the front, you call it DQ. Okay. And we talked about this: first in, first out, last in, last out. High complexity is the same as the stack. Okay. And then let's talk about the use cases for this. So for queues, we already learned about the callback queue, right? Callback queue, to recap, is when you have a function that calls a web API. So it invokes the function, it goes to the call stack, and then throws that to the web API. And then once the web API process, let's say, the set timeout, it doesn't go back to call stack right away. It goes to the callback queue, queuing system. And then the event loop now pushes that back to call stack. Another very good example is a messaging queue. And as Amazon, you already provide this type of service. It's called Amazon Simple Queuing Service, SQS. SQS. So SQS is Actually, the concept of using this is pretty simple as well. You have, let's say, a component that sends a message. I think I have the documentation link here. So you have your zoom in. This is your queue. Don't mind the different servers. This is your full queue. And this is your distributed system component. Distributed system, in layman's term, basically means that you have a lot of systems, but in the user, it looks like it's just one. So the message lifecycle, first, let's say you have one component. It sends the message to the queue. And then after it's in the queue, it waits or also have like a lifespan or visibility timeout and wait for another component to retrieve the message from the queue. Okay. And then message A queue then deletes it from the queue, and now A is missing. Okay. So component 1 is the producer of the message, and component 2 is the consumer of the message. Okay. Think of it as like when you're sending in requests and stuff in websites. Let's see. And this is used, I think I've heard a lot of developers using this as part of their technology stack to help with the communications of different systems. Okay, so for stacks, we already have an example with the call stack, right? The function call stack. When you do recursion, it keeps adding functions in the stack and then pops it out if it resolves or returns. Another way to use stack is the depth first search traversal, which we're going to talk about tomorrow for binary trees. Okay, let's show you some visualization and see if I can show you some code. Any questions? Pretty easy for now. The stacks and queues, yeah. It is really easy, don't worry. Let's see, visualization. Did I put it in? Visualization. Okay, let's go first with the stack. So with this visualization, we can just put numbers and push, keep pushing, keep pushing. Now we can just do another operation to keep popping, and popping. As for the code, we can show you the code. So first thing you need is you create a class of the stack because you want to instantiate and create your own stack, right? And inside of the stack, when you create a stack, you initialize it with just an empty array. So again, underneath the hood, it's just an array. And if I show you, let's say the methods for creating them, let's see. So this, like the push function, pretty easy. So the class stack would have a method called push. And basically in that method, the user should add an input. And it basically just pushes the item into the array. Again, to the stack, and again, underneath the hood, it's an array. So pop function is when you call your dad. No, if Basically, you also need to catch if the stack is empty or not. If it's empty, just sometimes you can throw null, or just put a string is empty, or you can be technical about it and say underflow. And basically, you can just return this, meaning the stack dot items, which is this, meaning the array, and pop. So funny, right? You created a function pop, but you're also using the API of an array. You're kind of like masking it or hiding it. Next, we would have the peak. This time around, we don't want to remove stuff. We just want to see the top value. And the way you do this is basically you do stack or this dot items, and then what is the index? The index that you want to see is this dot item dot length -1, which is the end of the array. Sometimes we also want to know if the stack is empty or not. Basically, you just return, this one returns a Boolean value. This dot items dot length, if it's equal to 0, it will spit out true, or if not, it will just spit out false. And as usual in data structures, we do want to check how they look like. So we always optionally create a print function. And now we can use this. So again, because stack is just a class, when we want to create a one, we can say let s equals stack, new keyword, new instantiation of the stack. And it needs nothing. The constructor needs nothing, empty. So we don't need to put any parameter for now. Next is we can console.log and check s. See if I should put this on the side. Spec console stack. Boom, empty. Okay, so we now have an empty stack. Underneath the hood, it's just an empty array. And let's say we can access now the methods that we created. We push the number 5. Let's log that out again. And then we have the item 5. We can push another one, 10. And now we have 5 and 10. We can try all the other APIs as well. Let's say let's remove this now. S dot is empty. Does not need any parameter. Returns false. But if you do pop, and pop, it'll be true. And if you pop again, oops, and let's say check the stack, this one should have been return underflow. Oh. So I could just console.log this one to check. Now it returns underflow. Okay, stacks and queues are, I believe, the easiest data structures to really implement, because that's how you implement this, and you can challenge yourself and like implement a stack using 2 queues, something like that. But at the very basic level, this is how you do it, and I don't really need to extend this as much. Okay. Now move on to queues. So in queues, basically, again, we just have an empty array. Create a class called queue and have an empty array. And let's say we create the enqueue function. the enq function. And we put item as the parameter, and inside of it, let's call the queue, which is this, dot items dot push, and then the element. Let's put that above here. And for DQ, so DQ, don't really need to a passive parameter because you want it to do an action. So if, say this, items, this is empty. And then you want to return again underflow, meaning there's nothing there, okay? Else you can use the shift API of the array, okay? Shift API is just removing, again, the element, because now it's weird. So if you think of an array, array is 0, 1, 2, 3, 4. Okay? When you push, it goes here. So now the front of your cube is basically the beginning of your array. That's why we're using shift API of that array. Keep removing the index 0, index 0, index 0. Because again, in the arrays, you start at the last when you push. Okay. Next is you can check the front. So create a front function. And then if, let's say, the front is, it's not empty or is empty, return underflow again. If it's not empty, return this dot items and the length of access node, again this one. Okay, we want to see the front, the one standing in line next to the cashier. Okay, it's empty is just basically asking is if the queue has any value at all or not. If it did store any value, and then print is basically just, let's just copy that. Print queue. Okay, now we can use this. Let's say we'll create a variable queue to assign a new instance of a queue. New instance using the new keyword. And then when we have that, we can check first if we did create that one. There we go, queue. And let's say the enqueue. To do that is first you access the object queue dot, and then the API, the functions that you created for the class, and then you can enqueue, let's say number 1, 2, 3. Oops. Element is not defined. The queue this dot item, this dot item, and queue this dot item. Okay, maybe a typo again. Let's go back there. Copy this code. Whoop. Whoop. Okay. Yeah, I believe there was a typo. And now you can have your array 1, 2, 3. Create another one, 2, 3, 4. And then let's say you want to dequeue. We should be removing the first element of the array. Now I should only have 3, 2, 3, 4. There you go. And we can also print the queue. Access that. Okay. Oh, it's returned, so I have to console that one. remove this. You should see more. Okay. Let's try to go back to hash. I think, did I show you? So, and, let's just show you the queue. And queue. And queue. The queue. The queue. Okay. Last, we'll go back to hash functions. Oh, hash table, creating your hash table. As you can see is, let's grab this code. Let's grab this code. Put that here. So first thing we've done is we just created a hash function, and in this hash function, we should have a string as a parameter, and the max basically means the number of buckets, meaning array size, and basically we just create your hash value in those in the array. Yep. And next, you create just a hash table function, and you have an array. The length is 14. And then now these are the functions that you created, like the stacks and queue. You have a function to add. And you have a function to remove. This is very similar to when you're accessing objects, updating objects. And you can look up. See if we can run this. See. Okay, let's try here instead. So, yep, I think that looks better. So the first thing we do in line 71, we created a new hash table and we added stuff. Okay, and then the next thing is we log that out and print the stuff. So we have the number 5 here, just logging out the size, and basically you have this buckets. Okay, and inside the buckets you would have array or key value pair. It's up to you. You can put linked list. Okay. Let's try to have a visualization hash table. Okay, this one. So look, it looks like an array, and we can add numbers, or maybe string. Let's say, no, it doesn't let us string. Hash strings. Apple, insert. So as you can see, it's computing. It's so hot. It's creating a hash code for the apple. Wow, it took so long. And banana, insert. Okay, to speed this up, I think we should do hash integers instead. It's way faster. Okay. So it's using the modulus of 13 to create its hash code. So basically, what this visualization is doing, we have an array the length of 13, right? And then that's why it's using the modulus of greater than 13. So whatever number we put, modulus 13, put it there. So 13 modulus 13, 0, it will be going to the 0 index. Should be, okay? So if it's 14, it should go to 1. Okay, let's do 26, the double of 13. Okay. So now what happens is they're just values pointing to other values. Okay. We'll dig deeper on this tomorrow on linked list. Okay. So there you go for AQ1. So now, even though it does not have here, let's say I want to look for the number 412, and then the hash function would know right away, oh, this is a number 9. I should look only here. Look here. Okay. Let's deal with, let's say, muddiest point. Again,
we're doing mine later.
Oh, okay. Stacks and queues, blah, blah, blah. Again, basically you manage to use stack and queues because you want to manage your data in a particular way. You don't want people just accessing it, all of them, right? So you want to maintain some order and reduce the flexibility. Also, why you don't want flexibility on some, because you might corrupt data, right? Let's see. Yeah, this is for tomorrow, the binary search. I think hash set, hash map, do hash table and TypeScript have something similar, or have something to do with hash set, hash map? They don't have a built-in general map type, so no. And I just posted some of the links here, so I'll just upload this. Next is, okay, binary tree node. Less frequently used caching. Yes, it's hash tables are used on that. I'm not gonna go deeper, but I also gave a link, and I'll just, off topic. Will we be talking about JavaScript integration into a web page? Whew, how I wish, but instead have a code for that, a very simple one. Where was that? Not this. For tomorrow, this one. Oh, no, sorry. Then let's go back here. Okay, first things first, this is DOM manipulation using JavaScript. And basically what this simple program do is input. You can input whatever here. And if you add a new line and you input again, it basically, when you hit the button, it converts it into an array. Voila. Okay. The code itself, not that hard. I can explain this. Let's dissect. It did require some adding of Bootstrap and Ajax, whatever. And CSS, you kind of know already this one. So in the body, we just have a class, right? No, we have a div, and basically we have this message. Just not do anything for now. Text area, we just have a placeholder with nothing as well. Input, we have the go, which is, we see this one, go. Go, Power Rangers. And then now we create our script function, script, which is just a JavaScript. It just means that, hey, can you look for the ID go, which is this one. And in the ID go, if I'm listening to that button, if there's a click, please do this function. In the function, what it basically does is, please look for hashtag input, which is the ID input text area, which is this. Please look for this area, these area. Okay, in that area, can you grab me the value and split them? Okay, and then basically just here, you can skip over this one, push them into an array. Okay, and now we just want to update the input field, which is what happened. When I hit click go, it removes the previous values there, which is this one, the val, and then add output text and just put a bracket. So actually, what happened here is they just output the value, and just to print it, they put the brackets. But it's still, yeah, it's still an array. Sorry. Let's see. I'm also gonna upload the code for this, so feel free to play around with it, and also the source of the code. DOM traversal. Hope we also did this, but it's not part of the schedule. So this one is very basic. We have the body. Our H1 tag, we have the first H1 tag have an ID of ID01, and the P tag, paragraph tag, we have the ID02. In our script, we just want to say that, hey, get element by ID 02, which is this one, dot inner HTML, which is this one. This is that one. Okay. Hey, can you assign a text for that one, which is what? Can you get the document.get element ID, which is this one, and the value inside of the tag, which is dot inner HTML, which is this one. Okay. So what we're expecting here is the P tag should generate the same text that we have in the H1. And there you go. This is an H1. This is a P tag. Okay. Next, let's see. Another way to access it with a similar one is using child nodes. This is part of the API. So because basically this is structured like a, better to show you HTML tags hierarchy. Something like, no, this one. Let's see. So now, I guess this is kind of like an intro for tomorrow. Like, this is a tree or a graph, whatever, and you have parents and child. So that's why a while ago we're asking the child. Let's go back first and go back to this one. So we said that, hey, get element by ID01, which is the H1 tag, and the child nodes, access that one, and the node value. Okay, which is, if you have the H1 tag, it's just the inner HTML actually. And then we should get the same output. Okay, change these. Yep. See another code. This one is different. This one, if you want to grab the HTML body, which I don't think there's a use case for it, but at least you can see your whole DOM. And let's try that one. Alert. And you can see it on the top, it just spits out an alert that includes all of your HTML file, includes all the tags. Okay. Okay, that's about it. Questions? Okay.